Ba-dum-bum-bum-bum-bum. I was basically chugging this when you were gone. We were taking that break. You take a break? All right, did you get some coffee? Mm-hmm. Yeah, it's because, I got a Roma Joe's. Pretty good. Mm-hmm. Better than that Dunkin' Donuts stuff. Okay, in the last video, we talked about that there are intermolecular forces, what they are. There are three different strengths of them. They're bracketed into three different types, and we went through two types. We went through the strongest one, the hydrogen bonding. You have to have lone pairs on nitrogen, oxygen, and fluorine, and they have lone pairs, and they're Lewis structures. Remember Lewis structures? Yeah, they have those lone pairs and shared pairs. And you have to have a hydrogen in a different molecule, and that's where the bond forms. Okay, those are strongest. Then we went to intermediate strength, where we had an ion connecting up to a dipole, like I would give you the example of sodium, floating around in water, connecting to a water molecule on one side of it. That would be an ion. That's not it's water, but it's not a hydrogen bond because it's not going to be a hydrogen from a different molecule connecting to a nitrogen, oxygen, fluorine from a different molecule. So a sodium connecting to an water is not hydrogen bonding. And there was an ion dipole. And then dipole. Water does that, but water is special because it's a strong dipole. Then it gets classified as hydrogen bonding. I didn't give you an example, though. I realized after I finished, I said, all right, well, wait a minute. I didn't give you an example of a dipole. Here's one. It's very simple. So NaCl, salt, good old high-quality made-in-America salt. This is going to have a positive side and a negative side. Chlorine grabs the electron from sodium, and it becomes more negative, and the sodium giving up the electrons more positive. And if you have a sodium molecule here, it is going to then want to connect with another sodium chloride right next to it. So that would be an example of a dipole connection. So sodium chloride connect to each other. A block of rock salt. Rock salt, if you ever look at rock salt, it's actually kind of cool under a microscope. It's these perfect little cubes. Perfect little cubes. You take salt, pour it into your hand from a salt shaker. Look real close. You have much better eyes than I do right now because I'm old. I'm like 130 years old. I was born in the 80s. Yeah, 130. The 1880s, that is. So you look at it, and you are going to be able to see these little tiny perfect cubes. If not, take a magnifying glass, perfect cubes. And what happens is these form perfect cubes with that intermolecular connection. And then down below here, you can get another sodium chloride in, which is the negative side. So the positive here, and the positive and the negative here, and it forms a solid. If you take this and put it in water, it dissolves. That's a whole different ballgame. Okay, so there's an example of dipole. All right, now it's on to the LDFs. London dispersion forces, or dispersion forces. I sometimes say these arise within. In other words, what happens is, occasionally, due to random electron motion around the nucleus, you will have more electrons on one side of the atom than the other. It's just random motion. So let's say that we have, put a bunch of protons. Well, let's do it this way. Here's the nucleus of an atom, okay? And it's got the positives there in the nucleus. Actually, let's make it carbon. It's got 6 protons. And it's going to have 6 electrons out here. It's got 2 of them in the first energy level, then it's got 4 in energy level 2. These things don't just sit there, nor do they just go boop, 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 boop in orbit. They move, groove, shake, and bake. Especially if they get excited, they jump up energy levels, they're moving all over the place. So they have what's called a probability cloud. The probability that these electrons are located in any one location at one time is this probability cloud. Well, it could be, just by random motion of these, that you get more dots on one side than the other. So over here on the left, I have a bunch of negatives, and over here on the right, I only have like 1 negative. And if that happens, then this side of the molecule becomes much more negative than this side. And since you only have 1 over here and a whole bunch of positives here, this becomes positive on that side. Now that would be a dipole. That is a dipole that arises within the molecule due to random motion. And that happens. So it's also called a temporary dipole. This is temporary. Okay, a water molecule is going to be a dipole, period, all the time, 24/7. Okay, never takes a day off, never goes on vacation. This would be very temporary. And of course, if this was not connected to anything or nothing around it, it would just shift back, and it would maybe in the next second, this side becomes more negative, and then it shifts back, and then this side becomes, so these temporary dipoles due to this random motion of the electrons. But if that happens, and there happens to be another atom hanging out over here with its electrons, this side is now positive. It might just be for a split second, but it's long enough to cause positive attracted to the negative electrons on this atom. And these are going to go, what's going on over there? Party! I am seeing what's checking that out. Check out the party. And these will be attracted to this side of this atom because the positive was induced here, was formed here. So that makes this would actually be called induced dipolism. This would be an example of induced dipolism, where this became a dipole just by random motion and forced this one, induced this one to become a dipole because the positive of this would attract those negatives, and now we have a negative positive attraction here, and we have an intermolecular force. It's called the London dispersion force when that happens. And this actually explains how things are non-polar in their gases can actually form liquids. So if you form a liquid, and this is we're kind of rolling into some properties and what these are going to cause, these forces, what do they cause? They can cause liquids and solids to form. Liquids and solids are formed because of intermolecular forces. Intermolecular forces dictate who's going to be a liquid, who's going to be a solid, and who's going to be a gas. And we usually talk about at room temperature because that's what matters to us most of the time. Okay, let's take a look at hydrogen. Or now let's go helium. Helium, okay, what they do in hospitals, okay? Helium is what they do in hospitals, they helium. Tough crowd. If I'm helium, I have 2 protons, 2 positives in my nucleus, and then I've got 2 electrons. They're buzzing around out here in the lower, down here close. They want to be in the first energy level. Sometimes they're not, sometimes they move. Well, what happens if one happens to shift to the same size as this one? Then what happens? This becomes negative, this becomes positive. If I have another helium over here, that's going to induce that helium to have its electrons shift this way. And now I can get the helium to stick together. Now that only happens at really low temperatures. If you want to liquefy helium, you have to go to really low temperatures and a lot of pressure. If you put a lot of pressure on it, you force those heliums close together. And if you really make it cold, the electrons are slowing down. So when they finally do shift to one side, I get 2 electrons on this one side, that gives enough time because they're moving very slow and they can't get back. That you can give you enough time to cause those 2 non-polar gases to stick together. But you have to have really cold temperatures and really high pressures for that to happen. But it does explain, the London dispersion forces do explain why you can get something which is non-polar, which is a gas at room temperature, to liquefy under really cold temperatures. And a lot of times you just need really cold temperatures to liquefy gases that are normally gases at room temperature. But when something comes something like helium, you need extra, you need to put pressure on it as well. All right, so anyways, what I'm doing here is I'm talking about what are called dispersion forces, and these are due to random motions. Now, there's a word on here, and I didn't make this up because I say, you're gonna go, that's not real. You made that up. Polarizability. Polarizability. What it sounds like a made up word. No. It's right here. Where did I put it? There it is. Polarizability. Oh, yeah, but you made it up and you put it on the sheet. You just made it up. No, if you don't believe me, look it up, okay? I wouldn't trust me either. I wouldn't trust me. Like, look at me. You don't trust me. Go look it up. Go. I'll wait. And while you're looking it up, have more coffee. It's almost gone. So good. Did you look it up? Okay, good. Thank you. It is real. I ain't making this up now. What that means is polarizability means the ability of an atom, due to random motion, to become a dipole, to have more electrons shift to one side, cause that side to be negative, and the remaining side where they came from be positive. Polarizability, some things are more polarizable, or that's able to happen to them easier. Well, what atoms on the periodic table would be more polarizable or easier to have more electron shift? The larger atoms. The larger you are, the more electrons you have. The more electrons you have, the bigger the chance that electrons have shifted more to one side than the other. Okay, if I'm helium, I only have 2 electrons. So, there's a chance that one helium will shift to the other side of the other helium. Remember, these don't like each other anyways, but the chance that can happen. But what if you're like Francium, the lower left part of the periodic table? I call Francium the little old lady who lived in the shoe. Had so many children, electrons, she didn't know what to do. She has so many electrons. She's huge. She's huge with all these electrons and these outer energy levels, and they could be moving all over the place. At any one period, at any second of time, there is a huge chance that you're going to have more electrons shifted to one side than the other, causing a negative and a positive side. That's a very polarizable atom. So the larger atoms are more polarizable. We will come back to that about what's called melting and boiling points in just a minute. Okay, so let me give you an example of London dispersion forces. You use it, well, maybe you don't, but somebody usually in the household is using London dispersion forces on a daily basis in the kitchen. I was about to say saran wrap, but I just did it. I just said saran wrap anyways. I was actually plastic wrap. I say saran wrap, I'm advertising for saran wrap because it's a type of plastic wrap. Okay, I get paid for that. I just got, 20 bucks every time I say saran wrap, saran wrap, saran wrap. Woo, 60 bucks. Woohoo! What was I talking about? Oh, yeah, plastic wrap. You take plastic wrap and you put it towards something and it sticks. I mean, it's annoying sometimes, right? Because it'll stick to itself. And you're like, what the frick, stick your hands like, ah. But it's meant to do that because what it is saran wrap is made so that it has a positive side and a negative side. And that is going to cause induced dipolism in whatever it goes near. So something could be hanging out like a ceramic bowl and you just put your leftovers in it. Okay, it's chilling, it's minding its own business. And here comes a piece of saran wrap. No. And that positive side of the saran wrap will cause your negatives to shift, and then boom, that's called induced dipolism. Okay, we're shifting those electrons, and so and now the saran wrap will, it'll stick to whatever it is you just put it on. So plastic wrap certainly does that very well, and it's very weak. I mean, you can just go, yes, I am so strong, and pull it right off. So it's a weak intermolecular force. Okay, that's a general going over of the different kinds of intermolecular forces, and some characteristics of these intermolecular forces are as such. Well, actually, you know what? This video, we'll keep it relatively short. We'll keep it at 13 minutes, and we'll come up with the next video going into characteristics of what this stuff does.